Good morning, everybody. As you already know, the school has closed the campus for today, so we will do our lecture virtually. As far as I know, nothing has changed about our schedule because our lab is not even until Thursday, and so we will continue normally on Thursday, but today we will do our lecture on work and energy virtually. So make sure you have your notes out so that you can go and fill in the blanks of your notes as I'm going through this PowerPoint. So let's go ahead and get started. Okay, so let's talk about work and energy. So this is going to be a pretty short lecture, right? We'll describe work and energy. We'll describe the differences between potential and kinetic energy, identify and describe power and how it relates to work and energy. We'll describe electrical power, and then we'll also identify and describe fossil fuels and renewable resources. So first, let's talk about what work is, right? Work is basically the product of the magnitude of a force, right? So the product of the magnitude of a force. So you can take a look here, and there's an equation that can be used to calculate work. And that equation is work equals force times the parallel distance, right? And that parallel distance is actually the amount of distance that the object has moved that you put the force on, right? We use big W for work, right? Not to be confused with little w. And then we use big F for force, and then the little d is distance, right? Which you already know that. So what's the important thing about work? The important thing about work is that you can put all the force you can onto an object, and if it doesn't move, then no work is done. The object has to change its position for you to have done work, right? So that's what's happening up here in this particular guy, with this particular guy. He's got this crate, and this crate is sitting right here. He pushes it across the floor, and now the distance from here to here, he's moved it a distance from here to here, so he's done work, right? So he can take this distance, measured by a meter stick or something like that, put that in D. He can then put in how much force he put in there, and then he'll figure out how much work he put in, right? And so work can only be done if the object that you are applying force to actually moves, okay? And so why is that true? That's true because if you look at this guy here, he is putting a lot of force on this brick wall, right? But this brick wall is really heavy and really strong, so it's not moving at all, no matter how much force that he puts on it, right? So if the distance is 0, right? If the d equals 0 because the wall did not move at all, right? If the d equals 0 because the wall did not move at all, and we plug in d right there, right, for the equation, the force, no matter what it is, times 0 equals what? 0. And that's why there's no work being done, right? That's why there's no work being done. Another kind of like counterintuitive thing to think about too is this situation here. So we have this lady here who's working on a lawnmower, right? And she's exerting a force, right? She's exerting a downward force, right? A downward vertical force right there. And then she's also exerting a forward force, right there, right? That's horizontal, okay? So the net force or the net vector is this right here. That's the net, okay? But interestingly enough, right? Remember what I said. Work is only being done when the object that you're moving or trying to move with the force actually moves, right? And so since this lady here is actually on a flat surface, a level surface, her work being right here, pushing the lawnmower down, right, is actually 0 because the distance that it moved vertically is 0, right? The d equals 0 for the vertical distance right here, right? So she's not doing any work in the vertical direction, right? But here in the horizontal direction, the lawnmower is moving. And so if the lawnmower is moving, it's changing position. Therefore, work is being done in the horizontal position. Now, think about it, right? If the vertical work right now is 0 because the land is flat, what do you have to do to actually do some work, right? In the vertical direction? Well, imagine then if there was a hill and then she pushed up the hill. Now she would be doing work in both directions, right? Because her vertical distance is changing and also her horizontal distance is changing, right? So that's the big thing, okay? The big thing is that there has to be a distance move. The object has to be moved a distance for it to have work, right? Work being done on it. All right, so go ahead and scan this QR code and answer this question. Which of the following is not true about work? Work equals force times the parallel distance. Work is equal, or W equals FD. or specifically, let's say big W equals big F times D. Mechanical work involves both velocity and acceleration, or all the above are true about work. Okay, which of the following is not true? I'll give you a second to scan that. Make sure you scan it too, because this will tell me whether or not you actually watched the lecture. All right, so what are the units for work? Well, the SI unit for work is the Newton meter right here, right? Also known as the joule. Interestingly enough, it's almost exactly the same as the joule that we find in energy, right? Like calories, and remember the joules from when we were talking about before. And then the British system for work is called the foot pound. Okay, and so this is not to be confused with the foot pound that we use for torque, right? So SI system, Newton meters, or joule for short, and then British system is foot pound, right? Not to be confused with the foot pound for torque. All right, so work. What does this actually have to do with? Well, work is always against something, right? You are always doing work against something, and so when work is done, we generally feel the other part of Newton's third law, right? Because whenever in Newton's third law, it says that every action has an equal and opposite reaction, if you remember that, right? So if you push up against something, something will push it back up against you. And if it doesn't move, that's because you are both pushing with the same amount of force, right? But if you have more force than what you were pushing, then the object moves, then you've produced some work, right? You've made some work, right? So what are some of the things that help you or work against you doing work? Well, first and foremost, it's gravity, right? Anybody ever go take a hike up a hill, right? And you're trying to go up a hill, and it's a lot of work, right? And you're sweating, and your heart rate starts to increase and stuff like that. It's because you're doing some work. You're going up a hill vertically and horizontally, right? You're doing work in both directions, both vectors. But gravity is the thing that is keeping you from getting that's holding you back. And so when you overcome gravity, you're putting more force into it than gravity has, and therefore you do work because you're changing positions. And then friction is basically that guy that's pushing that crate across the floor, right? Those are both things that work against work. Work against work. There. That's interesting. Work against work. In the specific case of gravity, of course, I've already told you this before, right? Where you can actually change, remember, the original equation for for Newton. Second law is F equals ma. Oops. F equals ma, right? And I was telling you how you can actually change that a to g, because that g right there is just acceleration, right? A is acceleration, and then g is the acceleration of gravity, which is 9.8 meters per second squared. 9.8 meters per second squared, right? And so what that means then is the little w here, which is weight, equals mg, mass times the gravity, which I told you that last time already, right? And so by the way, little w is weight, and then big W is work, right? I know we're running out of letters in the alphabet, so now you have to use capitals and lower cases, right? We can extend this even further by adding h in there, right? Because now the amount of work being done is actually equal to the mass, right, times the grams, right? Sorry, not the grams, the gravity times the height that the object was moved, right? The object was lifted. So now work in the vertical direction can be work equals the mass times the gravity times the height the object has moved. We've already talked about this before, but there's two types of energy, right? There's potential energy and there's kinetic energy. Again, I won't make you ever do any math regarding this right here, but that's the equation for kinetic energy, right? 1/2 times the mass times the velocity squared of the object. So when you're up high, way up here, right? You have a lot of potential energy. You had to do work to get up there to begin with, so you better have a lot of potential energy, right? But then as you go down the hill, right, your potential energy starts to decrease because you're going down the hill, and then your kinetic energy is increasing because you are moving faster, right? Because kinetic energy is the energy of motion, and then the potential energy is stored energy. So interestingly enough, right, you actually have to do work to stop an automobile, right? And to figure that out, that's the braking force times the distance, right? Here, work equals FD again, okay? And then we can do all this math, which I don't really care about you doing, but I just want you to know that if you've doubled the velocity, right, your braking distance will be 4 times, right, what it would be if you didn't double the velocity. And then if you tripled the velocity, right, your braking distance would be 9 times what it would be if you weren't going, if you're going just, normal speed, right, normal velocity, right? So here you can see in this picture that if you're going about 32 kilometers an hour, right, 32 kilometers an hour, your braking distance is only 8 meters, right? But if you go 64 kilometers an hour, your braking distance is actually 32 meters, right? 32 meters. So, for this question, go ahead and scan the QR code. If the velocity is doubled, braking distance is doubled, tripled, quadrupled, or no way to tell. So let's talk a little bit more about potential energy, right? So again, potential energy is really based on position, right? It really is based on position. The higher you are, right, the higher the object is, the more potential it has, right? And that's like I was talking about before, how if I were to fall off the side of a house, the side of a deck, right? The higher I am, the more potential I am, potential energy I have, right? But the lower I am, the less the potential energy I have, right? And so what all this stuff says right here is that potential energy, right, actually equals the mass times the gravity times the height the object is. Again, because you had to do work to put the thing up there to begin with, right? I had to go up to this hill, right, before I flew off the deck, right? So the thing to remember about potential energy, right, is that it's all based on the vertical position, right? Gravity stays the same, right? Gravity stays the same. So you can say then that potential energy, right, or EP, equals the mass times gravity. So my mass, for example, times gravity, right? And then the height, and that's the amount of potential energy you have. So another interesting thing about potential energy is that it's not just based on the height that an object is, it's also based on the change in height, right? So if you recall, this triangle here means change, right? And you may be asking yourself, what does that matter? That matters because I already told you that if you were to be here, so pretend that this is like, sea level or the ground right here, right? If you were to do the work and put an object up here at, say, 50 height, right? 50 height, whatever that unit is, right? They're just 50. Let's just say 50 feet, right? You did the work to put the ball all the way up here, then you would have that much potential energy, right? 50 feet, okay? If you put 50 feet up there. But say you dug a hole, right? And you dug a hole 50 feet deep, right? Well, you would still have the same potential energy as you were if you were up here because you did the work to go dig down to 50 feet, right? And so it's not just really about the height, but it's really about the change in height, right? How much does that ball or that object or you have to fall, right? And you could be on the ground and then fall into a hole, and then you would have potential energy before you fell into the hole, or you could be at the top of a mountain fall, and you'd have a lot of energy at the top of the mountain, but then when you fell, you'd be turning into kinetic energy. So potential energy really deals with the change in height, right? Because from up here, the 50 to the 0 feet, right, is still 50 feet, right? But then from the 0 feet to the negative 50 feet, which is when you dug the hole, it's also 50 feet, right? And so when you put in 50 here as the change in height, the potential energy is still the same, right? And you can think about it like this. You did work to put the ball at the top, which is 50 feet high, and you also did work to dig the hole to put the ball at the bottom of the 50-foot hole, right? So in both cases, you have done that much work, and because you moved the ball in the vertical positions, and the vertical positions were identical, right? Whether they were up on a hill or down in a hole, and therefore the potential energy is identical. So go ahead and scan this and see, if you know the answer to this, right? What are some examples of potential energy? Water being held back by a dam, and energy found in a chemical bond, a yo-yo before it's released, Or all these examples are potential energy. I'll give you a second to scan that. All right. So that takes us to talking about power, right? Talking about power. What is power? Power is the rate of time of doing work, right? So you can take P for power right here, all right? And power equals work divided by time, or work, which is big T, divided by little t, which is time. Not to be confused with big T, little t. Sorry, I just got confused there. Little t, right, which is time, right? Big T is actually temperature. So don't confuse those two. So work divided by little t, time, right, gives you power. Or FD, which is force times distance moved, divided by time, gives you power, right? And so most people know that about a watt. What is a watt? A watt is a unit of power. So 1 watt actually also equals 1 joule seconds, right? If you recall that that the unit of work is a joule, right? And so now that you have seconds involved, right, or time involved to make power, that's going to be 1 joule second, right? So 1 watt equals 1 joule second. Okay. For example, a 100 watt light bulb uses 100 joules per second of electrical power, or 100 watts, right? 100 watts. So here you can see a guy who's got a weight at the bottom here of this little pulley, and he's pulling it, right? He's pulling it right there. And it took him 1 second to lift it off the ground and move it that high, a distance of 1 meter, right? Okay. And so from that, you can see that there's a distance, right? A time and a force, right? A distance, a time, and a force, right? So what you can do is you can multiply the distance times the force, which is 1 times 1, right? And divide that by, 1 times 1, and then divide that by 1, and you can see now this person has done 1 watt. Has done 1 watt of power, right? 1 watt of power was used to do this. So the British system actually uses a different unit called the foot-pound, which we talked about earlier. So for work, right? So what, and then for the British system, we talked about that earlier about the British system using the foot-pound, not to be confused with the torque foot-pound, but the British system work foot-pound, right? But the interesting thing about that is power is actually equal to foot-pounds per second, right? Just like before, it was joules per second, but now, since we're using the British system, it's foot-pound per second, right? But an even more common way to think about power is horsepower, right? Whenever you're looking at a car and its engine and how fast it goes and all that kind of stuff, right? That's horsepower. 1 horsepower equals 550 foot-pounds per second, or 746 watts, right? You may be thinking to yourself, what the heck? Where did the horsepower come from, right? Well, the horsepower comes from the fact that a horse, right, can pull, right, a weight on a pulley, just like that other guy, right? That's 550 pounds up 1 foot in 1 second. And that's where horsepower comes from, right? So 1 horsepower equals 745.7 watts, or 550 foot-pounds, right? That's where that 550 comes from, right? A horse pulling a 550-pound weight, right, up 1 foot in the time of 1 second, and that's a horsepower, right? That's a horsepower. So if you ever wondered where horsepower has come from, in your house, I mean, not in your house, but in your car, that's where it comes from, right? So we're just talking about the car. What about inside of a house? Well, inside of a house, power is, again, is what we use, given in joule seconds, right? And so if you look at the unit here that's on this electrical meter, it actually says kilowatt hours, right? So we have a unit of work, which is kilowatt, divided by the time, hours, right? And so that's how you get the power, right? That's what the electrical company uses, right? So the electrical company uses a kilowatt hour to determine how much electricity you use, and you should be well aware of that now because electricity bills are crazy, right? Electricity bills are crazy. So let's talk about the different types of energy that are available, right? There's a few types. First, there's thermal energy, right? And thermal energy is related to kinetic and potential energy at the molecular level. That's thermal heat energy right there, right? We also have gravitational potential energy, which is what we talked about a lot. This is the gravitational potential energy that's stored from an object's vertical position, right? We talked about that a lot recently, just in this lecture alone. That's me being on the second floor and getting tossed off the second floor. Energy level is energy that, or sorry, electrical energy is energy that's associated with electrical charges. Chemical energy is in molecular bonds. Radiant energy, which is electromagnetic rays from the sun. You're feeling this right now because I went outside today and it was like in the 20s, but I still felt warm because I was in the sunlight, and the sunlight has radiant energy and it makes you feel warm, even though the temperature itself is actually in the 20s outside. Right? If you were to step in the shade, you'd feel those 20s really easily. We also have nuclear energy, which is fission and fusion. What is fission? Fission is the breaking apart of larger nuclei, whereas fusion is smaller nuclei being put together. Both of those cause energy, right? We'll talk a lot more about all these things later, right? Like we'll talk about nuclear energy soon in the nuclear physics section. We'll talk about radiant energy a lot as well, right? And chemical energy. But those are some different types of energies. We also have fossil fuels. Fossil fuels include oil, gas, coal, and what are those? Those are actually the fossils of living organisms, right? And so they get buried underground, and they have a lot of energy in them, right? Stored up, right? From sun, solar energy, and chemical energy stored up, right? Oil usually comes from marine organisms, right? Gas comes from marine organisms as well, and then coal actually comes from terrestrial land plants that are fossilized, right? A newer thing that's coming out right now is methane hydrate, right, which is a crystalline form of natural gas. That's still research is still being done on that right now. Research is still being done on that, right? So, which of the following is not a fossil fuel? Is it oil? Is it nuclear energy, gas, or coal? Which of the following is not a fossil fuel? All right, so just some cool charts to look at real quick. U.S. fuel consumption. Of course, in the United States, we use the most in oil, right? That's oil and also gasoline, okay? And then close second is natural gas, coal. Coal is actually what most of the country uses to get energy, like electricity, right? Very little bit of it is actually nuclear power. We'll talk more about nuclear power later, of course. It's very interesting. And they're renewable sources like solar power and that kind of stuff, wind energy. We barely use any of those things. So, fuels for electrical generation, again, 49% of our electricity comes from coal. Some of it comes from gas. We'll talk about how that works later. Nuclear energy. And then here are some this is hydroelectric, which is renewable, not very many. Petroleum oil, and then we use petroleum oil for automobiles, obviously, not for electricity. And then other renewable resources, barely any, right? So yes, we use tons and tons of coal to produce our electricity. Energy consumption by sector, right? Industry uses a lot of energy, right? 41%. Transportation, and then commercial, residential makes up the rest of it, right? So what type of fuel is used most in electricity generation? Is it coal, natural gas, nuclear energy, or hydroelectric? All right, so now let's talk about some alternate energy sources or renewable energy sources, right? Basically, renewable energy sources are energy sources that are not dependent on fossil fuels, right? We don't need to have fossils from a gazillion years ago to make energy, right? And renewable energy is what we need because we're going to eventually run out of fossil fuels, right? So here are some of them. We'll go through each one individually in a second, but we have solar, hydro, wind energy, tidal energy, geothermal energy, and biomass. Let's talk about each one of these. So hydropower, this is pretty obvious what hydropower is. It's basically potential energy, right, that is stored from water being held back by a dam. And then whenever we need electricity, the dam's doors open, right, and water rushes down. And there are these water turbines that turn, right? These turbines that turn from the water rushing down, and that generates electricity. We'll talk about more how that works when we get to like electricity itself and motors and stuff like that. But yeah, that's how hydropower works, right? And so this is the Flaming Gorge Dam in Utah, right? The only While this is a really good source of energy, there's some bad things about it. There's always like environmental leakage, right? Ecological leakage, and then also when you have to build a dam, that's kind of loss of agricultural land, right? We also have wind power. Uh, there are a few, wind power is exactly what you think it is. It's just using the power of wind to turn those big windmills right here, right? And those big windmills turn a turbine, which generate electricity. But there are a few problems with it. First and foremost, you have to have wind. Sometimes there's no wind, so it's hard to store up enough energy to get you between the times there's not enough wind, right? But also another thing, they're not particularly aesthetic. They take up a lot of space. But the good thing about them is they do have very minor environmental effects because they're on a very thin pole and they send up very high, right? So very, very, very little environmental effects. But they're just not very pretty. And I mean, I guess the most important thing is you have to have wind for them to work. And sometimes there's just not any wind around, right? Solar power. So everybody knows about solar power. I'm sure you've had people come to your house before asking for you to buy solar panels, right? Very, very promising future energy source, right? Hell, in my neighborhood, there's people with solar panels all over the roofs, right? Um, and so, again, the only problem with solar energy is just like with wind energy, you have to have sunlight. So you have to store the energy in batteries. And if you have a prolonged time with no sunlight, you might run out of batteries. You run out of energy in your battery, so that's sad, all right? That's a problem. But also, they take up a lot of space. Like solar farms take up a lot of space too, so that's a problem. We also have geothermal energy. So this is actually in Iceland right here, where they use the hot temperatures below the ground to make steam, and the steam turns turbines, and those turbines generate electricity. The problem is that it's very specific where these things can happen, right? You can't have a geothermal energy generator just anywhere, right? You have to be at very specific places, right? Depends on large natural change in temperature being present and accessible, right? And exclusively used on Iceland. This is one of the cool ones here called tidal energy. Basically, it's like a windmill, except it uses ocean or water currents. These particular windmills are bidirectional, or windmills, sorry. These bidirectional, these, what do you even call these? I don't even know. But anyway, water can go backwards and forwards through them. They turn those little propellers and generates electricity, and that's what you get electricity from. What's great about these is that they're underwater, so you can't really see anything, right? It's not very it's aesthetically pleasing because you can't really see them. They're underwater, and so I don't know why we don't use more of this, because out in the ocean there's tons of currents. It's probably distance is probably the problem. Having to get them, travel the electricity, having to have the electricity travel all the way from the ocean all the way to different localities is probably the problem. But this is a pretty cool one here, right? So this tidal one right here, this tidal generator right here, is actually in the Rance River in France, and it's been generating electricity for 160 since 1960s, right? So that's pretty cool. I think tidal energy is pretty neat. Then we have biofuels. Again, so this is also renewable, right? This is where we use corn, sugarcane, or other plants to make ethanol, right? And then ethanol can be used as energy, obviously, right? So, because I don't know if you know this, but when you go get gas, there's, unless it's no ethanol added, it's got at least 10%, or at most 10% ethanol in it, right? Because ethanol can be burned as a source of energy, right? So yes, it is in gasoline. ethanol can be mixed with gasoline and used as a fuel for cars, called gasohol. I actually didn't know it's called that. And then the last one here is actually called biomass energy. Biomass energy is interesting because what you do is you take, it's like a cycle. We use CO2 in the air to feed plants and trees, right? Those plants and trees die, right? When they die, we burn them, right? And we burn them, right? Or when they decay, both burn and decay, they they make steam, and then the steam comes up and becomes CO2 again, right? It becomes CO2 again. So that's pretty cool. Basically, getting rid of all our waste, right? By burning it and turning that waste into energy. Pretty neat. Anyway, that ends today's lecture for today, right? And so our schedule doesn't change. We will continue on Thursday as usual. Have a nice day. I'll see you guys on Thursday.